This lesson, we're going to multiply like bases. Before we do that, though, we need to define what a base actually is. We've studied monomials, and actually monomials have bases when they have exponents. I've already alluded to basically what we're going to get into. In order to have a base, you pretty much need an exponent as well. Like, we've talked about like monomials, they need to have the same variables and exponents for a monomial. Now, like bases basically just mean they need to be the same, okay? Let's go ahead and look at the components of, in this case, this would be a monomial. But let's look at the difference between a base and an exponent. The base is just basically the number below the exponent or the variable. So a base can be a number or a variable. In this case, it's x, but it could also be 7 or 2 or whatever you want it to be. It could even be a fraction. The exponent is the number up and to the right of the base. So you basically can't have one without the other, okay? Without the exponent, you really wouldn't have a base. It would just be a variable at that point. And you certainly can't have an exponent without a base. So again, they go hand in hand. The exponent's up and to the right. The base is whatever is below the exponent. Like I said, it could be a variable or a number. Now for a monomial, the exponent can't be a variable. If the exponent's a variable, that's an exponential function. That's something completely different. For the gist of this lesson, we're just going to be focusing on exponents that are whole numbers. Okay? We might have a few with decimals, and of course the rules are the same. Actually, we do have one with a negative number. The rules are the same, and we're going to learn what that rule is. So basically what we're trying to get at is, how do you multiply like bases? Let's take a look, and I'm going to show you exactly what we're going to do and why we do it. Let's say that we have 3 squared times 3 cubed. Notice these do have like bases. They're both 3. Now, if they weren't both 3, we wouldn't be able to apply the rule we're about to do. But because they're both 3's, we can do it. Now, 3 squared is the same as 3 times 3. That's what squared means. It means multiply 3 by itself. 3 cubed means 3 times 3 times 3. So if we have 3 squared times 3 cubed, we really have 3 times 3 times 3 times 3 times 3. We're multiplying 3 by itself how many times? 5 times, right? Which, yes, is 243, but what I want you to focus on is the fact that when we break this problem down, we end up with 3 5s being multiplied by themselves, which is 3 to the 5th. Now, if we look at the original problem, how does this relate? Well, what we could have done is just added the 2 and the 3 to get the 5, since we had 2 3's and 3 3's. This, in essence, is the rule we're getting at. When you have like bases, you're going to end up adding the exponents, and we're going to take a look at a few more examples to make sure that indeed that rule works. If we have 2 squared times 2 to the 5th, this is a times, we'll talk about this plus in a second, but 2 squared, in fact, I'll make this a little bit more definitive. Remember the dot means multiply. 2 squared times 2 to the 5th. So 2 squared is 2 times 2. 2 to the 5th is 2 times 2 times 2 times 2 times 2. Again, we see that we have 7 total 2's that are being multiplied by themselves, so that's 2 to the 7th. But what we really could have done again is we could have just added 2 plus 5 to get 7. This is why we add the exponents when multiplying like bases. In this case, the bases are both 2. Because when we add them, we get the exponent that we would have gotten had we done it the long way and broken the 2's down, into single 2's and then multiplied them 7 times. Answer is 128. But what we're getting at is the rule of adding the exponents when the bases are the same. One more, we need to do a variable. If we have x to the 4th times x to the 5th, let's break this down. X to the 4th is x times x times x times x. X to the 5th is x times itself 5 times. We see we have 9 total x's. That's just x to the 9th. But what we could have done is just seen that this is 4 and this is 5. 4 plus 5 gives you 9. So when multiplying like bases, just add the exponents, and that's why. I've shown you why. We've broken it down. Now let's go ahead and look at some examples. X to the 5th times x to the 9th. Well, since we don't have to break it down anymore and we know the rule, all you have to do is add the exponents for step 1. 5 plus 9 is 14. We are going to get into a few more steps for further examples, so let's take a look at those. If you have a negative exponent, you're going to move it to the denominator. Now, I'm going to talk about that later, the reason why we do that. And in fact, once you move it to the denominator, you make it positive as well. Okay. So we're going to do an example where we have to do that, and again, I'll talk about later why we do that. But for now, just know that if you have a negative exponent, like x to the negative 7, you make the 7 positive and you put it under 1. And then after that, you simplify. And so actually step 2 and 3 could kind of be the same thing, because ultimately that's what we're doing, is simplifying when we take a negative exponent and we move it to the denominator. That leads us to example 2, which isn't going to include those steps. We have y to the 5th times y to the negative 9. Since the bases are the same, we are going to add the exponents. Now just think about this for a second. If this was y and this was x, we could not do that. In fact, we can't do anything with that. We wouldn't be able to multiply them, but because the bases are the same, we can add the exponents. So what's 5 plus negative 9? It's negative 4. All right, so what do we do with that? Well, like I said before, for step 2, you make the exponent, you move the negative exponent to the denominator, and then you make it positive. So basically, since it's negative 4, we're going to put it under 1 and make it positive, so it becomes 1 over y to the 4th. Again, in a later lesson, I'm going to talk about why that is. It has to do with the fact that a negative exponent actually means division. And so like 3 to the negative 4 actually means 1 divided by 3 divided by 3 divided by 3 divided by 3. So you divide 3 4 times. That would be 1 over 3 to the 4th. But again, we'll talk about that in a later lesson. We'll certainly see that come up a lot in future examples. All right, final example. We have z to the negative 4th times z to the 4th. Well, since both the bases are z, that means they're like bases, we can add the exponents. Negative 4 plus 4 is 0. Now, we've already talked about this before, but what is anything to the 0 power? You remember before, anything to the 0 power is 1. Okay, so step 2 doesn't apply here because it's 0, it's not negative, so we don't have to flip it or anything. But like I said, anything to the 0 power is 1. Okay, so the final answer is 1 in this case. In other words, z to the negative 4 times z to the 4th ends up just being 1. And that's going to happen anytime you have, let's say, x to the negative 7 times x to the 7. In fact, I'll write that one out so you can see. But anytime you have like the same base and the exponents are opposite signs, you're actually just going to get 1 back. Okay, because it's going to be x to the 0, which is just 1. So that might be a little shortcut you can use next time you see an example like this. So that's it. It's pretty simple. When you multiply like bases, you add the exponents. And if the exponent is negative, you make it positive and put it under 1. Again, I'll talk about in a future lesson why that's true. If you have any other questions about multiplying like bases, let me know.